Since the number of moles of gas in a container is directly proportional to the pressure, we can create a useful ratio to convert between partial pressure and the number of moles of a particular gas. This useful fraction is called a mole fraction, and it is exactly what it sounds like, a fraction of the total moles. We use the Greek letter chi to denote a mole fraction, and we use a subscript to designate which gas the fraction describes. In this case, we're talking about the moles of thing number 1 divided by the total moles. You can also write this as moles of thing 1 divided by all of the other individual types of moles added up together. In the previous video, we rearranged the ideal gas equation to isolate the mole variable, and we will substitute that expression in here. If we factor out the V divided by RT from all of the terms in the denominator, we can cancel out the volume, gas constant, and temperature variables. This means that our mole fraction is equal to the partial pressure of interest divided by the total pressure. We can make two more useful forms of this equation for problem solving later. Now, Dalton's law of partial pressures and mole fractions are not too bad on their own, but most textbooks have some really cool application questions that require you to incorporate other concepts as well. For example, let's do a problem that I've modified from the Cheng and Goldsby textbook. A mixture of methane and ethane is stored in a container at 276 millimeters mercury. The gases are burned in air to form carbon dioxide and water. If the pressure of the carbon dioxide is 342 millimeters mercury, measured at the same temperature and volume as the original mixture, calculate the mole fractions of the gases. The first thing I realized when I read this question was that there is very limited information about the state of the gases. This makes me feel like we will have to use some fancy ratios to figure things out. The next thing I see is that I'm going to need to write two different balanced chemical equations for my combusting gases. Now, I don't know how many moles of gas we are starting with, so I need to tackle this problem like I would approach an average atomic mass problem, with loads of variables. I'll write each partial pressure with a capital P with a subscript for that chemical, and use my mole-to-mole ratios from my balanced chemical equations to find a useful proportion. This means that the pressure of CO2 directly from the methane source is going to be the same partial pressure as it started with, and that the pressure of CO2 from the ethane source is actually going to be twice as much as it originally started at. Now, what I know from Dalton's law of partial pressures is that these two pressures add up to the total pressure of carbon dioxide given in the prompt. We also know that the original partial pressures added up to 276 millimeters mercury. Now that we have two statements that are true with two variables, we can solve this system of equations using your favorite algebraic method. I like using substitution personally, so let's give that a go. We have, another way of saying the partial pressure of CO2 is 276 minus the partial pressure of ethane. So I will plug in 276 millimeters mercury minus the pressure of ethane plus 2 pressures of ethane equals 342 millimeters mercury. Then we can simplify by taking away one of these and that 2 to get 276 plus the pressure of ethane equals 342. Simplified, that means that the pressure, or rather the partial pressure of ethane, is 66 millimeters mercury. This also implies, if I resubstitute back in, that the partial pressure of carbon dioxide is 210 millimeters mercury. Now that we have the partial pressures of each gas, we can use them to answer the real question, which was the mole fractions in the original gas mixture. So the mole fraction of carbon dioxide is 210 millimeters mercury divided by 276 millimeters mercury, which means that is 0.761. And the mole fraction of the ethane gas would be 66 millimeters mercury divided by 276, which gets us 0.239. Now this was one of the more difficult problems I came across, so you should definitely do a few relevant practice problems before moving on to these harder examples.